Now, if you go back and look at our generalized development of the energy balance and the material balance and momentum balance and even the electrical flux balance, we had started to speculate that among all these fluids, there is this generalized relationship that we have a first derivative in time, we have a first derivative in convection, and there was a second derivative term that related to diffusion or dispersion. So we had speculated that perhaps a fluid is inadequately described by any specific property like mass or energy or momentum. And you'll find in the literature that there is this kind of speculation that's been going on for several decades. And this has shown up in this field of analogies. So in analogies, we recognize that there are these similarities in mass, heat, and momentum transfer, and there have been attempts to exploit these analogies so that we could estimate one constant from another. So, for example, if we review the so-called Schmidt number, so Schmidt was obviously a researcher who contributed greatly to chemical engineering, and the Schmidt number is named after him, which is in effect the viscous diffusion rate divided by the molecular diffusion rate. So in other words, the viscosity divided by the mass, so it's in effect the momentum diffusion divided by the mass diffusion. In other words, viscosity divided by diffusivity. And there is a density correction because viscosity is written more in terms of a mass flow and diffusion is written more in terms of a molar flow. So we think of this density factor being more as a correction between different dimensions here. And so we really have the momentum dispersion concept divided by the mass dispersion concept. So I'm trying not to say diffusion here. If I said diffusion, then it would be specific to mass. So let's think of this abstract concept of dispersion. So dispersion is the thing that tends to cause things to spread out. And if you think about the three cases, right, in mass, the thing that causes our molecules to spread out is diffusion. If you think of momentum, the reason that our fluid gets dragged around and that there's disturbance, even if one section is separate, is not directly influenced by the presence of a wall, for example, then that's viscous drag. So viscosity is the momentum concept where our velocity is spread around. And if you think about the thermal case, conductivity is what tends to cause our thermal energy to dissipate or to disperse around the system. So we are in the Schmidt number looking at the momentum dispersion divided by the mass dispersion. And there you've got the viscosity divided by diffusivity, and then we are just correcting using the density to translate to mass here. So that's the Schmidt number. And by the way, these numbers have emerged over decades. So it wasn't automatic that it was observed that the fluids had these relationships and that it was realized this would be a useful thing to do. It was observed over time that if we developed the Schmidt number, then we could scale our processes quite well. So, for example, if you had two fluids and the only difference was the viscosity, then we found that there was a relationship with some of the other variables. And so if we wanted to achieve the same, for example, diffusivity in that fluid, then we would simply change that the viscosity, then that would give us a new Schmidt number, and then that would help us to figure out how to change the geometry of the system to accommodate this different viscosity. So it might mean that we need to increase the power requirements and so on. So if we wanted to design a system where the competition between the mass dispersion and the momentum dispersion was the same, then this would be the way to do it, right? If we knew what the Schmidt number was for a given process. Likewise, with the Sherwood number, we here instead have the competition between the convection transfer rate and the diffusion transfer rate. And here, this in effect is your mass transfer rate divided by your diffusion. And in fact, these are similar concepts, right? The mass rate, this is actually in a way an approximation to your diffusivity, right? Your characteristic length in this case is, of course, the film thickness. So to understand this well, you need to go back to your film thickness, to your film theory, and the characteristic length was the position at which we achieved 99% of the bulk value. In this case, the spatial dimension is not going to be the film thickness. More typically, this is something like a diameter in a pipeline or something like that. So in the Sherwood number, we are trying to maintain the same mass transfer conditions. So if we want to achieve a certain mass transfer rate, then we would estimate the Sherwood number for the given situation, and then for the new situation, we would correct by the size of the system, and then we would know what conditions to apply to get the same Sherwood number. So Sherwood number, that has to do more with your correction in terms of the space of the system. In the Prandtl number, we are comparing momentum and heat. So here you can see momentum, you've got your viscosity contribution, and then with heating, you've got your conductivity and your heat capacity. So if you look at your momentum diffusivity, we had said just now that's your viscosity divided by your density. And then if you look at thermal diffusivity, typically your conductivity divided by your heat capacity. And depending what version of heat capacity you use, whether it's mass or mole based, you might have to correct with the mass density. So if you have, then the densities can cancel and we can rewrite it like this. So the Prandtl number, another useful one, which helps us relate your momentum and your heat transfer. The Reynolds number, probably the most famous one, that's of course relating your convective flow to your diffusive flow. Excuse me. So here we have the diffusion, not the diffusion. Here we have the convection rate. So here you can see your velocity, for example, in a pipeline, and then the density and the diameter of the pipeline. So all these are related to how fast the bulk fluid is flowing, and then that's also related to the tendency of the fluid to attract itself, and the forces that influence the surface tension and so on in the fluid. So all these factors influence the state of turbulence of the fluid. So if the Reynolds number is quite low, it might be in laminar flow, then it goes through a transition zone, and then it becomes turbulent. So with the Reynolds number also, these numbers all tell us the state of the fluid. And again, if we think about a situation where we have a pipeline and it's of some diameter, and then we want to consider another pipeline, so we want to change the diameter of the pipeline, then if we want to maintain the same type of flow, right, if it was, let's say, laminar, for example, then if we keep the Reynolds number the same, so if we are changing D, and we might not be able to change the density or the viscosity, so those are intrinsic properties of the fluid, so we might not change that, but we certainly can change the velocity in the pipeline. So if we are changing the diameter, then we could change the velocity in such a way that we keep the same Reynolds number. And that might be useful because maybe we want to have the same type of flow. We might want laminar flow, or we might want turbulent flow. So it might be that we are designing a pump for that pipeline, and we are expecting that pump is designed for turbulence, whereas we are suddenly sending laminar flow. So those kinds of issues can result in improper behavior and lead to failure of all types. So we would rather, if we know that the fluid is behaving in a particular way in one pipeline, and if we want that same behavior, then we try to keep the Reynolds number constant. And so you see these dimensionless groups, they help us to scale our systems. And a typical application would be in the lab. We might have, or in a pilot plant, we might have figured out a good process. We've got our pilot plant working, and it's producing our product in the right way, and we are happy with the fluid flow profiles and so on. And then when we think about going to a much larger scale, so if we want to go from producing a kilogram per hour, if we want to produce hundreds of tons per day, and we are suddenly creating much greater sized units, then if we simply keep these dimensionless constants constant by respecting by using these relationships, then we have a good that's a good indication that we are going to get the same type of behavior. So these parameters will show that they have other applications, but they are quite useful in particular for scaling up our systems and for design purposes for things like that. So the analogies that we talked about, right? Remember in the generalized balances section, we had talked about that there seems to be an underlying connection among momentum, heat, and mass transfer, and even electrical flux. So there seems to be an underlying relationship among those, and now we are starting to exploit that, and it's helping us to actually design our systems far better. So that's one application of these analogies. And this part is just showing a bit about where the relationships come from. So the next application of these is that we can actually find relationships among these numbers. So this is the Sherwood number, that's the Reynolds number, that's the Schmidt number. We said each of these is helpful in their own right. But the other useful thing is that if we can find relationships among these groups, then we have some hope of estimating some of these constants. And you see, some of these are not so easy to estimate. So, for example, the mass transfer coefficient. Now, we had talked about a way to estimate it. We said if we know the diffusivity and if we had the film thickness, then we could estimate this value. However, it's almost never the case that you can estimate a film thickness. And the moment you change the geometry of the system, the film thickness will change also. So it's not typically easy to get a number for Kc. And even some of these other numbers, even the viscosity, there are some well-established equipment items for measuring viscosity, but we don't always have access to that equipment. We know there's a fair amount of difficulty involved in estimating our diffusivity as well. Even conductivity, and well, we could pick any of these and say it's not that easy to get. And that is the case. None of these are easy parameters. So the moment we change the geometry, or if the fluid mixture is strange in some way, then those numbers are all going to change. And what helps us then is if we have a relationship among these dimensionless groups, then we could find one group, we could find a number for one group when given the other groups, and then we could use that to estimate the unknown constants. So for that to work, though, we have to have good functions here. And you see, these relationships, they vary from situation to situation. So sometimes if your fluid is flowing at a high rate, then there's a particular relationship that you can rely on. On the other hand, if the temperature is different or if the nature of the chemicals are different, then sometimes another relationship has to be used. So in the notes, you'll find some analogies or some specific situations where we can estimate some of these numbers. And in fact, all of it is based on solutions to the material and momentum balances that we've been talking about. So you have some descriptions, especially of the Blasius solution. So some of these are actually derived. So some of these relationships are derived from solving those material and momentum balances. For example, we have the Chilton Colburn analogy. So here we have the so-called J factors, and you can relate. You can see here these are mass transfer / momentum type factors, and you can relate those to the heat factors. So here is an attempt to cancel out all the influences such that you get equality. So you can find equality between the mass parameters and the heat parameters. And so it's actually quite incredible that these constants are actually related to each other. So again, we can see that in the fluid, there is something more intrinsic than what we have been led to believe. And so we can find that the overall heat transfer coefficient is related to the mass transfer coefficient. And then that greatly simplifies any of the work that we have to do. So these analogies, we will be reviewing some of them in the tutorial and taking advantage of those relationships to find, to get estimates of our numbers and be able to solve our equations. So you can work through some of the examples given in the notes, and then of course we'll go through more examples in the tutorial.